Today, we are going to start with a review on graphing rational functions. So if I give you the function of x over x squared minus x minus 12, and we want to graph this eventually, you need to figure out some important information in order to graph it. So I would like you to spend a little bit of time finding those important informations and then trying to graph this polynomial, or rather this rational function. Right? I will pause while you are working. Now that we've had a little bit of time, row 1, person 1. Andrew, could you tell us one piece of information you can get out of this? X minus 4 and x plus 3. So if you factor out the denominator, that's what we end up with. And what did you get? What kind of information did you get out of this? So here we know now that our vertical asymptotes are at x equals 4 and at x equals negative 3. Awesome. Would you like to call? Row 6, person 4. Will, could you tell us another piece of information you found? So our domain is just the opposite of what our vertical asymptote was. So it's just that x cannot be those two values. Nice. Would you like to call in somebody? Row 2, person 5. Amila, could you tell us another piece of information here?
Okay, I thought of this. I'm not sure it's right though.
Okay.
So like, it still works for like digit 3. It's like, if it's bigger on the bottom, then the horizontal asymptote has to be 0.
Yes. So for a horizontal asymptote, we have y equals 0. Because if we look over here, our degree is bigger on the bottom. And I like that we're using bigger on the bottom. If we use bigger on the bottom, how can we shorten that? Bob? Bob's a cool guy. And because Bob has an O in the middle of his name, he likes O's or zeros. So Bob tells us that we know that our horizontal asymptote here is at y equals 0. Okay. Emil, would you like to call on somebody? Row 2, person 1. Ryan, can you tell us another piece of information here? Like, for example, could you tell us the x-intercept? Zero. Because if we just plug in 0 for y, what does x have to be? 0. Alright? And then, if we want the y-intercept, what do you think the y-intercept is going to be? Also at 0? Because if your x-intercept is at 0, 0, you have to have a y-intercept at 0, 0. Okay. Do we have any holes? No. So we don't have to worry about those. So now we've got all of this information, and we can graph it. And when we graph this, we have our two vertical asymptotes, one at 4, one at negative 3. And we have a horizontal asymptote at y equals 0. And what important points do we need to add? What's an important point we need to add to our graph? Olivier? So we already added those because those were our vertical asymptotes. What other point have we not added so far, though? We haven't added 0, 0, right? And that's right here. Now from here, if we want to figure out how to graph this, we need to be able to figure out, are we going to be graphing in this area here, or are we going to be graphing in this area here? Do we know at this point? We don't. So what is the first thing that we should do before we start graphing? What do you think, Greta? Alright, let's use the number line, excuse me. And if we put our x values, we know we had one at -3, and we had one at 4. What other important x values did we have? One at 0. So we know that we can't cross at -3 and at 4, because those are asymptotes. But we could cross at 0, because that's a 0 point. And we need our function to go through 0, 0. So now I have to figure out our behavior. If we are looking for behavior in this section over here, that means that we need to have an x value that is less than -3. If we need a number that is less than -3. Ryan, what is one number that you would use that is less than -3? -13. All right. If we use -13, and we go all the way back up to our original equation, and we say -13 squared minus -13 minus 12, is that denominator going to be positive or negative? If we have -13 squared, that's a pretty big number, so I'm going to guess it's going to be positive. So we're going to have a positive in the denominator. What are we going to have in the numerator? Negative. Negative divided by a positive is a negative. So we're going to have some negative behavior right here. All right, now we need a number that's greater than -3 but less than 0. Okay, let's use 1. If we use 1, we need to figure out if this is positive or negative. And then for this section here and this section here, we need 2 more test cases. So take a few moments, run those test cases through, pick a test case, run it through your function, and determine whether you will get a positive or a negative y value. I will pause while you work. All right, we have our 3 different test value areas. So row 5, person 1. Could you tell us what you got when you plugged in 1 for your test value? Up here. When you plugged in 1 to the x values here, did you get a positive or a negative y? Yes. Got a negative y. Here. All right. Raise a hand, or show of hands. Who agrees? Who thinks it's positive? All right. I believe this one is positive in this instance. We have to be really careful about positives and negatives here, because if you have 1 minus, or it's a -1, right? Oh, that's right, because I said 1 and 1 is not in between these, right? So the 1 would go here, and this would be a -1. So you are correct in saying that if you plug in 1, it will be negative. Right? And then if you were to plug in -1, then it would be positive. Awesome. We squared that away. All right, we need 1 more test case. So row 3, person 5 comes back up to you, Greta. Could you tell us what you used as your test case? Okay, and then what did you get?
I have positive.
Positive. So from this, from our number line here, we know that we have to be in this area here. We have to be in this area here, in this area, and this area. So if we were to graph this, over here we don't have any points we need to go through, so we're just going to stick to the asymptotes. Over here we also don't have any points, so we're going to stick to our asymptotes. But here in the middle we have this point right here. And it goes from the positive, where we stick by the asymptote, to the negative. And since we need to go through this point, we have to connect them. Now at this point, wait a second. We just went through a point at 0, 0, but don't we have an asymptote at y equals 0? How could we cross? Didn't we say can't? All right. If we think about asymptotes, when we had the original case way back on the first day, where we had this graph here, and we were looking at how to find an asymptote, we said we can look at where an asymptote would be, because if you look at the end behavior here, then you know that the limit of the function as x approaches, and here, if it approaches at 0, and here we're approaching from the left or the right? The left side of our graph. So we're approaching from the left side of our graph. Then we know this overall goes to infinity. So we know long term, it's not going to touch 0. So that's how we knew there was an asymptote. Keywords there are long term. If we are looking up here at this part of our function, and we were just looking at long term, is our long term behavior crossing the asymptotes? They're not. But right here in the middle, it is allowed to cross because it is not the long term behavior. It is merely the behavior at that point, and we know that it has to go through that point because it is an intercept. To my knowledge, cases like this will not happen with vertical asymptotes. It tends to happen mainly with our horizontal asymptotes. So I would be careful of your horizontal asymptotes, but if there is a case where it does cross, that is okay. Yes? So in the case of parabolas, you would probably end up having some kind of y-intercept that would end up being your vertex. So if you had some kind of parabola, because of the y-intercepts, you would probably not cross the horizontal asymptote. It is only cases where you have some kind of cubic or quartic or odd degree where this sort of behavior occurs. Okay, that one was a little tricky, which is why I wanted to do it in class instead of assigning it for homework. So, what I would like to do next is, yesterday for homework, what did I say? We had 2 problems, so that you should probably do them, right? So, if you could pull out those 2 problems, you're going to grade them. And while we grade them, I'm going to pause the recording. Moving on to today's content, we are learning about this idea of proportionality, or basically when 2 things are proportional. If 2 things are proportional, what does that mean about them? Turn and talk with your neighbor for 20 seconds. Turn and talk with the neighbor that's behind you or in front of you. And ask them, what does proportional mean? Okay, I'm hearing a lot of good mathematical terms in here. Could somebody, a brave soul, tell me what they talked about with their partner? Yes? Ratio. So it's kind of like a ratio. Exactly. And so, things that are proportional are linked. And because they are linked, we can relate them to each other using equations. So, the first type of proportionality is if 2 things are directly proportional. If you're directly proportional, for example, if I had A and I have B, and they are directly proportional, that just means that they're equal to each other. And there could be some kind of constant that is also present. So I'm going to say that they're equal to each other, but there's some kind of constant. I'm going to write a K for constant, because constant starts with K. Everybody knows that. Okay? The next case would be if two variables, A and B, were inversely proportional. When you think of inverse, think kind of like the inverse function. So if we have an inverse function, what does that mean? Y is equal to... If I want the inverse of x, how would I write the inverse of x? X to the negative first. Or how else could I write that? 1 over x. So if two things are inversely proportional, that just means that it's 1 is equal to, so one of your variables is equal to 1 divided by the other variable. And instead of a 1, there could be some kind of constant. So I'm going to use my K for constant again. And the final case we would talk about is if some variables were jointly proportional. If you have jointly proportional, that means that you have at least 3 variables. So you would have A, B, and C. And if they're jointly proportional, all that means is that A is equal to B in some form. But A is also equal to C in some form, which means that B and C are on the same side and they're just multiplied by each other. So A is equal to B times C with some kind of constant in front. Fun fact about using K as a constant. K is used as a constant for multiple different physics relations. So if we look up here at these 4 examples, and you look at these 4 examples, you notice how this first one says Hooke's law? Hooke's law is a physics equation. It's my favorite. So if we have Hooke's law, and it says that F is directly proportional to X, then we see that F is equal to X with our constant K. If we wanted to do the same thing down here for Ohm's law, you might say, I've never needed to use Ohm's law. Who here has ever built a circuit? Or they've lit a light bulb with using a battery? You might not have known it. You used Ohm's law. Okay. Ohm's law right here is basically using the current, I, and it says that it's directly proportional to the voltage, or the power, which is V. And so if it's directly proportional to the voltage V, where should I put the voltage? If I have I and I have V, do they go on the same side? Do they go on different sides? What do we do? What do you think, Caroline? Okay. They're on different sides. And is I just equal to V? Or is it 1 over V? If they're directly proportional. If it's directly proportional, I is going to equal V with some kind of constant. It also says that it's inversely proportional to something called the resistance. And the resistance is basically, it kind of stops the current where it is for a little while. And it's basically a light bulb has resistance. So if you look at the resistance is inversely proportional. So is it going to go next to the V, or is it going to be dividing the V? It's inversely proportional. Is it going to be multiplied by V or dividing V. I will indeed be dividing it. So we're just going to put R down here. Don't need this anymore. Okay. Also, fun fact. Did you know recently they redefined the kilogram? Isn't that weird? I've been using kilograms for forever. But now the kilogram has a different meaning. Because the kilogram, before, it used to be this hunk of metal. And they took that hunk of metal and they locked it in a vault somewhere, in a vault. And they said, okay, we're going to touch this as least the minimum amount possible. Because we want to keep it in its pristine form. But then they've taken it out 3 times since they created it many years ago. And the 3 times that they took it off, they noticed that the actual kilogram was slowly decreasing in weight, which is not good, because if you have a standard, it should stay that standard always, right? So they recently redefined the kilogram, and instead they redefined it using laws that you find in nature, and one of them is called Plancks Constant. And if it's a constant, what letter do you think they use for it? K. So now the kilogram is based off of constant K, which is pretty cool. All right, moving on for today. Let's see. So many things to do, so little time. Let's just do a kind of like ease off on material, and let's do something that's kind of familiar. So for your homework last night, you had to solve a rational function for x, right? What if instead of solving it, we said we had some kind of inequality instead? If we have an inequality, what we want to do for the inequality is we want to figure out where this rational function exists. But in order to do this, we need to be able to solve for x, just like we did before, right? So, first step, if we are looking at an inequality, pretend it's not an inequality. If I just said this was equal to 1, and I wanted to solve this for x, can you do it? Take a few moments, see if you can solve this out for x. I will pause while you solve. We set these equal so that we could solve for x. So, if we are trying to solve for x, row 3, person 3. Caroline, could you tell us the first step you did in solving for x?
I multiplied both sides by x squared plus 1.
So we end up with 3 minus 1 is equal to x plus 1 when we multiplied both sides by x squared plus 1. Okay? Would you like to call on someone? Row 4, person 4. Zach, could you tell me what your next step was in solving this? All right, we are adding 1. So we are left with 3x is equal to x squared plus 2. Would you like to call on someone? Row 2, person 2. I just got 2 doubles in a row. Okay. Subtract 3x from both sides. So we have 0 is equal to x squared minus 3x plus 2. Dice or call. Row 6, person 2. From here, we want to solve and find x. All right, we've got x minus 2 and x minus 1. So if we have these two, that just means that x is equal to 1 and 2. Show of hands, I got here. Okay. If we did not get here, yes, it is an inequality. At this point, we're just treating it like it is equal so we can find our important x values. And why are these x values important? What are they? Are they our roots? Our x-intercepts? Our solutions? They are. So we have found our zeros here. And because we found our zeros, now we can create a number line. And on this number line, if we put 1 and 2, we wanted to figure out when is this inequality here less than or equal to 1. At 1, what are we equal to? If we put in 1 for x, what do we end up with? Well, here I have a 3 minus 1, and here I have a 1 plus 1. So don't I end up with 1? So here I have 1, and here I have 1. But now I need to figure out, am I going to get 1 in here? Or am I going to get 1 out here or out here? Or am I going to get less than 1 in those places? So what would be, if we look over here, we want a number that is smaller than 1. So we need to do test cases again. What's a good test case to have that's smaller than 1? 0 would be the easiest. So let's look at 0. If we put in 0 for x, we have minus 1 divided by 1. So negative 1 divided by 1 is negative 1. Is negative 1 less than 1? Right here we got negative 1. And negative 1 is less than 1. So I would say that this is a good place to be over here. We want this area over here. Okay, what's the number between 1 and 2? 1.5 sounds like a nice number. If we put in 1.5, 1.5 squared, is that 2.25? Sounds good to me. So we have 2.25 on the bottom, and we have 3 times 1.5 minus 1. So it looks like we're going to have some kind of number up there. Let's see. 4.5 minus 1 is 3.5. So we have 3.5 divided by 3.25. Is that greater than, equal to, or less than 1? It's greater than, so we don't want this middle section, because we want to be less than 1. All right, now we need a value that is greater than 2, so let's use 3. If we use 3 here, we have 3 times 3, 9, minus 1, 8. 3 squared plus 1. Are we going to get a number that is greater than, equal to, or less than 1? Take a few seconds, work this one out, and decide. Is it going to be greater than, less than, or equal to 1? I will pause for those few seconds. Okay, we've had our few seconds. Shepard, can you tell us what you got? We do want this section because was it less than 1? It was less than 1. So if we're looking at this and we want to write the sections that we would like, we would go from negative infinity to negative 1. Do we include negative 1? We have a less than or equal to sign, so should we include negative 1? We should. Thank you. So we include negative 1, and we include 2 all the way to infinity. Okay. I did one problem like this, and it was on your homework. So I would like you to do another problem. I would like you to do number 17 for homework. Yes, Greta. What would be a solution? It would be Yes, good catch. So this is not a -1, this is a 1 right there. You are correct. I saw the -1 instead of the 1. Yes, that would be -infinity to 1 because 1 is the zero, or the solution that we found there. Okay. Going back to homework for today. Homework for today would be number 17. It will be, I would like you to try number 29. It is a word problem, but I believe in you. You can do it. And these are like the proportional material that we went over today, so I would like you to do the first 4. You have a few minutes. I bet you could get these 4 done before you walk out of the classroom. Alright, that is all the material that we are going to be covering for today.